everyone. Thus far, we've been focusing on normally distributed continuous data. And we've learned how to calculate the process capability indices, CP and CPK, from this normally distributed data. But now we want to look briefly at calculating capability, or at least an equivalent metric, using attribute data. Now, attribute data is discrete data where the specification is set up so that values within the specifications are considered good, acceptable, and those outside of the specifications are considered defective. Learning objectives today are to explain the differences between a capability analysis for discrete data compared to continuous data, and to perform a capability analysis for attribute data by calculating our defects per unit, our defects per million opportunities, and converting these to a sigma capability. So again, CP and CPK. These are capability metrics which compare continuous distribution to given specifications. And we assume then we have, for these metrics, a normal distribution, and a process that produces all of its data within all of these units within these specifications is said to be capable process. And of course, we've learned about CP and CPK. CP compares the variability allowed, or variability in the process, to the variability allowed in the specifications. And then CPK is also doing that, but allowing to see if our process is off target and therefore out of specification. But what do we do if the data is not continuous? So here on the left, we have, for example, measurement length, so continuous data. And what we say here is the spec is here at 80.003 centimeters, and anything lower than 80.003 is acceptable, but anything on this side greater than 80.003 centimeters is out of spec. This side we're in spec. Now for discrete data, here we have, for example, the count of the number of errors, for example, on a typed page. So we have here one error here. I mean, we have several more instances. We seem to have quite a few instances with 5 errors. Is just an example here. And we've given a specification that the maximum allowed errors is 6. So this means anything greater than 6 is considered out of spec. It's considered unacceptable. And here on this side, anything less than 6, or we could say greater than or equal to 7, less than or equal to 6. So we have to deal with this in a different way, because clearly we can't just go ahead and calculate our yields as we did before. So how should we handle this? First, a little review. We discussed then the 3 most important probability distributions useful for describing random variables encountered in quality engineering. We had the binomial and Poisson discrete distributions, and then of course our familiar normal distribution for continuous random variables. So let's look again at the binomial and Poisson. So the binomial distribution is again used to assess the proportion of defective items in a subgroup, or the fraction of non-conforming items. So its distribution, or its PMF as we called it, is given by this equation where we have 2 variables, n and p, where P is the probability of a success, so 1 minus P is the probability of a failure in one trial, and P then lies between 0 and 1, it's a probability, and we have then a sample of size n. And this means then our random variable x can take the values of 0, 1, 2, up until n, because when the trial is repeated then n times, you can have from 0 to n successes. And where do we use this? Well, if you're given the exact probability of an event happening, and you're asked to calculate the probability that this event will happen k times out of n, then you can use the binomial distribution. And for an example, if a production process is known to produce 3% defectives, what is the probability from a lot of 100? There is exactly one defect. So, what is the probability of performing exactly one defect? N, there's your one defect, there's your probability of success and your probability of failure. And we've done that then in the previous lecture. A Poisson distribution looks slightly different. It considers the total number of defects counted, for example. And a random variable x is then said to have the Poisson distribution with this equation as the probability mass function. And so again, the Poisson variable, the x, will take on values between 0, 1, 2, 3, etc., up to a very large number, ideally infinity, and it has one parameter, which is this lambda parameter. So how can we recognize in a Poisson variable? The variable must be countable and can take only values from 0 to infinity. And some examples, for example, are machine failures per month, the number of faults per year in a cable, for example, lightning strikes during a 30-minute storm in Oklahoma, the number of blemishes per shirt, the number of pinholes per square foot of galvanized sheet, something like that. And if you have a mean or an average probability of an event happening per unit time or per page or per mile, cycle, etc., then you're asked to calculate the probability of an event, of n events happening in a given time, or a number of pages or number of miles cycled. Then you can use your Poisson distribution. So for example, a chemical plant experiences on average 3 accidents per month. So here we have our lambda variable. What is the probability that there'll be no more than 2 accidents next month? Then we can use our probability distribution for lambda, our Poisson distribution for lambda. So process capability then for discrete data is assessed then differently from continuous data. And here what we're going to go through are some key assessments. These are often used to give a comparable metric to this capability, the sigma capability that we learned for the normally distributed data. First, we have to confirm that we have a stable process. That would be the first step. Now, we are going to do this in course 2 under control when we look at control charts. So for this session, we're going to assume that we have a stable process. And this means that the process produces outputs which are consistent and they're not changing due to any trend or isolated events. So that we're going to take as given for this lecture. We're then going to take the measurements of our attribute data and record the number of defects. And as we'll see in the next examples. So just remember, a defect occurs during any process step when the outcome of the process step is not your expected outcome. And this expected outcome is, of course, specified in advance. And a defect then is a single non-conforming quality characteristic of an item. But as we learned, an item may have multiple opportunities for a defect. The term defective then refers to items which are considered unacceptable due to one or more defects. So using this data, though, we'll calculate then the defect per unit and the defect per million opportunities with our discrete data. And we'll convert this then to a sigma capability. And of course then check, are the customer requirements met?